Okay, so I think we can continue a little bit on chapter 14. So last time we have seen how we can get the idea on the limit when we approach the xy to certain points, and then if we want to show the limit is not exist, one way to show it is we are going to let some path. Okay? We are going to let some path that is going to be our references. Okay? I hope you get what this means. It means that every time we have this, limit, it means that how we can approach this point 0, 0, it actually can be many ways. We could take the, for example, take it maybe path at x-axis, which means when y equals 0, or take it in y-axis when x equals 0, which gives you the idea that, okay, then we are going to let the y as a constant. For example, here is 0. Well, you could use another number that to set up to this evaluation. You could make it maybe 1, maybe 2. But I think 0 makes sense because for our computation, it will be much more easier. As long as we can see some satisfactory and equaling these functions, and then we could get some conclusion. And of course, when we say that there are many ways to approach certain points, those ways must be in domain with the same domain with the function itself. Okay? For example, here, then this denominator should not be equal to 0. That's for sure. And then let me go for one more example, and we go for the partial derivative. Okay. So suppose that we have limit approaching 0, 0, and suppose that we have x, y. Maybe two more examples. So this one is x, y, and okay. But the question maybe just does this limit exist? Okay, if we take the path, okay, so choosing the path, so first perhaps we say that we want to have an x-axis, the path is x-axis, so taking y equals 0, then we get the f. Suppose that this is the functions. Okay, suppose that this is a function that's naming as f. So suppose the functions will be x and 0. Then this will give you the 0 over x squared, which is 0. Right? And when x equals 0, it will give you the same conclusions, which is 0 over the variable, which is the y squared. And of course, from here, the statement will be 0. So arguably, we have two similar value, 0. But we are not done yet. That if we want to make sure that this is going to be the final answer, we need to make sure the other path will works as well. So let me write here, although we obtain identical limits along two axes, x and y, it is not showing that the limit is 0. What we can do, however, take another line, taking for example y equal x. Okay. So we can substitute x with y or substitute y with x. Okay. So let's say we are substituting y with x. So this will be fxx, which gives you, this is x squared, and the denominator becomes 2x squared, which gives you 1/2 as a result. And since we obtain different limits along different paths, then limit doesn't exist. And by doing this, I hope you get the idea that depends on the functions. Like, there are many ways the function can be represented. So if we have like maybe different functions, and if you see the polynomials, the degree that the function has, you may try something different. You may try maybe using parabola for the path. You may using another line. Maybe not only y equal x, you could also try y equal just mx, or maybe some number that can be solved through the function. So you could try some equation as well. Okay. And I think the easiest way to be broken for each steps, we can start from a very simple path through some line, and then maybe increasing to some polynomial, maybe increasing again to some cubic. That is something that we can try. Okay, now when we have this limit, proving the limit doesn't exist, now we can move to the continuity in the function of two variables. Now it will be very, very similar to what we have in calculus 1, if you remember that. So we can call the function of two variables continuous if the limit exists. Okay, so the limit exists, and it will be equal to the function itself. So this means the left part here means the limit exists. You can find the limit, have some finite value. And when we plug in AB only to that function, this will be having the equal value, which means that there are nothing, you can imagine like a hole, like we did in calculus 1, there is no hole in between of this function. Or now, it's not only functions, we can describe the function as a surface. So the surface will be a full solid surface. There's no hole in between. And now we can say the function will be continuous on some b. B could be understood as our, in our case here, it could be understood as the xy plane that we project from the surface to the xy plane. Okay? So all the b, or we could say the domain of this function, they must be also continuous, okay? So at every point. Okay? At every point.
Continuous means that it's derivative, right?
Continuous, but not necessarily
Not necessarily.
But to be able to derive, need to be continuous, yes. So let's have some observations. So if you see here, since we have some special denominator here, which this x squared plus y squared should not be equal to 0. So if the points, okay, so if the points, let's say, so the point, if we have point 0, 0, so at the point 0, 0, the f will be discontinuous, right? Because it's not defined at that point. So we can write, however, we can write and make some restrictions for the domain. Okay, so f will be continuous on its domain, which we can set as D, as long as the xy is not equal 0, 0. Which means we can work for every number that are available, right? And sometimes, to make it easy, the function could be described in the piecewise defined functions that will have directly saying that, okay, this will be equal to 0 if it is at 0, 0. And then the other places, you need to have, it will be, you can define this in other places as long as it's not 0, 0. Okay, so we have this piecewise. So here, although the piecewise could be understood as we have two different equations here. So G, in our case here, so G is defined at 0, 0, but because limit xy approaching 0, 0 of this x squared minus y squared This is the same as the previous example that I've shown, but because this is not exist, okay, so because this is not exist, not existed, then G is still discontinuous. Okay. So although we write in terms of piecewise, this is actually the same thing as we write the previous example, but this is more nice and clean way to write a function. But if you look at this equations and we try to take the limit itself is not exist. That means it's still not continuous. Although we write and force the piecewise to have 0 at this point, still it's not exist because the limit doesn't exist. So first you need to have existing the limit, and the second you need to have similar value at its function. Okay, now if you see example 9, we could check the limit first. So checking the true sum path, we can try y equals 0, we can try x equals 0, we can try y equal x, and also perhaps we could also try the y equal x squared. Okay. So if we try this, you will see that I will not write completely, but you could see just from when we substitute one of them. So maybe try y equals 0, you will see it's 0, and then you will see the denominator we have x. So it will be the f x 0 will be 0, and then the f 0 y, this is also 0. And if you have the substituting y with x, you have this will be let's say xx. So this is x cubed and then x4, 3. So we see that we have 3 over x, or squared, sorry, it's x 2x x squared, right? So this will be x on the top is more than the bottom one, so it should be if we take the limit as it is going to be 0, this will be equal to 0, right? So this will be equal to 0, and we suspect that maybe we have an existence in limits. So we try the y equal x squared. So we have here is x and x squared. So 3x4 And then x squared is x4, so x squared plus x4. This will cancel. And we see that we have, if we put x as 0 in limit, we see that this might be still having here. So this will be also another 0, 0 over 1, right? So this will be another 0. So this is a sign that this could be having a limit. But how to make sure that we have limit? There are some ways, but I will show you just maybe at least two methods. Okay, so if we remember the epsilon delta. Okay, now in two variables, okay, we need the epsilon positive, and then we want to find a delta that is positive, that is if we have positive delta, that we define the delta using the Pythagorean. If you remember the Pythagorean, the distance between the x and y. And then we have, so then we have the distance between the function and the origin. Let's say the origin will be a 0. This should be less than epsilon. So we would like to find how much is delta needed to satisfy the epsilon. And then we also know that since the y squared is positive, so we can write the x squared is, it will be always less or equal x squared plus y squared, okay? because the y squared is positive, because y squared is positive. So we could write, so the x squared over x squared plus y squared, okay, the maximum number that it will get is at least closer to 1, or it will not exceed 1. Okay, it will not exceed 1. Okay. So imagine that since this is a y squared, this must be positive. So this must be larger. So if we have this larger here, this will be not going to exceed 1, right? So let me write here. Maybe this is not needed. Example 10. So let me write here. Therefore, x squared, and I will make a absolute value of y to make sure that it stay in the positive value. X squared plus y squared, this must be less equal 3 absolute value of y. Okay. So from this expression, I will take 3 both sides, okay, and then take the absolute value of 1. Okay. Just to make sure that we are in the same inequality with this last one here, which is to have another expression with 3 and y. And this could be getting from 3 square root of y squared. Okay. And since y squared can be plus y or minus y, that's why we have the absolute value. We need to make sure that it's still positive. Which means that this, let me write, maybe right here. And this y squared must be less equal of this x squared plus y squared. So, since we get the same expression here with the delta that we have, we could imagine to connect this 3 with our supposed to be delta, we can get multiplication of 3. Okay, so multiplication of 3, we can take that as our epsilon. So we can choose the delta is epsilon over 3, and we have the delta in between of this, and then from the epsilon that we have, and for sure that we have from our equations, this must be less equal 3. Oh, I'm missing out 3. Sorry, it should be 3. Okay, so 3 and then x squared plus y squared. Okay, and since this is going to be our delta, and the delta is epsilon over 3, so we can write this. This is less 3 delta, which is 3 multiplied with epsilon over 3, which gives you a perfect 1 epsilon. Okay. So since this is true, then by the end, thus the limit equaling to 0. Okay, so we can use the precise definitions to prove that we can have the limit, and especially for something that is easily to be observed, especially if the structure is easily to be play with the delta, which is this expression. You could try that as well, as long as it is easy to be conceived using this delta. If not, there will be some other arguments how to choose the delta. Usually we can choose using some scalar notation like this. Sometimes we can also using the a polynomial structure, but that will be a little bit complication in process. So basically, if we can exchange this part here, the delta that we defined, I think it should be easy to prove in epsilon delta. So what we need is all the epsilon, all the delta, we assume all is positive because they are the distance that is going to be perfect. Okay, I think this is from here. Okay,
No, 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 no.
let me from here. Okay, from here. From here. Okay. So what our idea, the delta in the function of two variables, we need to understand that this will be the main point. Okay? This is the delta that is going to be Pythagorean, the distance between the 2 points. Distance between 2 points. The epsilon is still the same in calculus 1, but now we have two variables, function of two variables. So what we need is, this is expression of our function. Okay? Okay. And then, this L is our, so we assume that since we try some path, all is 0. So we assume that L is 0. So that is, we put 0 here. So we need to make sure that this epsilon, when we choose some delta, and we try to find a way to find the delta through this square root of x squared.
Why is this square root? Where have you taken it?
Pythagorean. Pythagorean. Triangle.
Triangle.
Yeah. Get it? Point. X, Y.
It's hypothetical.
Pythagorean. Pythagorean. Hypotenuse. Hypotenuse. Yes. Yes.
But where is this? Where is this? Hypothetical.
In the xy plane. Draw.
Okay,
Well, you can see this is the drawing. Okay, that's the hypotenuse. Okay. Okay. See this one. Okay. Okay.
Yeah, I understand that our radius is hypotenuse of a triangle.
Yes, that is the x squared and y squared. And actually, we have a and b, but our question is if a b is approaching 0, so we put 0. But that's one b. That's right. Get it? It actually we just connect this to our function here, and we need to find, can it be multiplied with each other, or we can find how to find the multiplication of the relation between epsilon and delta.
But delta is delta for our variables and epsilon for our z's. I mean,
Function is okay. So here, maybe let me write more, just giving more expressions that this means. Let me write here. The 0 means assuming that L is 0, and here AB is approaching 0, 0. So if we can prove the limit exists, back to the continuity. So if we can prove the limit exists, then this function will be continuous.
Why do you write the epsilon more than 0? It's always no.
Yeah, I'm just writing. Yeah. You can see.
Okay, we need to find the delta.
Yeah.
So we take from our definition of
Yes.
limit
Yes.
if 0 less
Yes. Yes.
roots,
Yeah.
if where x zero and less than delta, then consequently our mod absolute value of this function minus zero, function minus our possible limit.
Yes, possible value.
Less than epsilon. Okay, and next step, x squared less than x squared plus y squared.
Well, basically, this is just a mathematical inequality.
Where almost. You want in this inequality
Hmm?
try to compare to like to do from this inequality like left side
Right side, left side, and right side.
the left side similar to our function.
Yes.
The same.
Yes.
And
Yes.
this way you will find our epsilon.
Yes.
And our epsilon is free
Yeah.
free multiply
Yes.
square root.
Yes. So basically, we say that we offer that the absolute or the delta should be the absolute of the tree, so that this will be equally matching with our this epsilon. So this will be the
Wait, our epsilon why our epsilon why our epsilon is free multiply y absolute y. And this our epsilon less than something. This free multiply square root of summary of squares.
Yes.
But I mean, no, I don't get this point. Why do we need this inequality? It's a right inequality.
This one.
Yes.
This is something that we want to approach, and we get it from this inequality that we know that the expression should be less than this, which means that this y squared also less than equal with the exponent plus y squared.
Okay, it's true. And
Yeah.
what?
Yeah. Actually, it's n up to here, but we want to make sure that we get our delta expression, which is this one. So that's why I'm making another inequality. But for sure that if we have this, then we can match up with our supposed to be the absolute. Okay. Okay.
Wait, you artificially
What?
I mean you artificially bigger. You artificially
No, that is
bend it.
no.
Our epsilon from this inequality, left inequality is 3 multiply square root of y squared. And like we want to put it similarly to our delta. So if we add the square root x squared, it's gonna be not so exact. I mean, it's gonna be expanded, but similar but this way we can connect our epsilon with delta. Anyway, nothing will be changed fundamentally.
Yes.
So, and then we can compare our free delta with epsilon. No, our delta with epsilon. Absolute of function minus possible limit. Absolute less than our expanded epsilon. Expanded epsilon is consequently less than free delta from in the beginning. And we understand that they are similar, so delta like a little equal to approachingly equal to delta.
Like an approximation.
Yeah, approximately equal to epsilon over yes, epsilon. Free delta approximately equal to epsilon. So, and if this all works, then we have then
Yes.
this limit exists.
Yes. Actually, like an absolute delta, it's not something that you could get easily understood in the first explanation. Like even for me, after I graduated, like undergraduate, finished, I'm still having not really good for understanding the actual number. So if you don't understand, as long as you know the fundamentals, that's okay. It's not easy to describe because epsilon and delta is actually a value that is, I would say, like quite abstract. But anyway, I would like to end this part with the definition of the partial derivative. Okay, the partial derivatives. Oh, so consequently, I forgot to say here, this function, they are continuous. Okay. Okay, so let me write here the partial derivatives of two variables, a function of two variables. Okay, let me write first. Okay, if f is function of two variables, let x vary and y fixed, then let's say we have a new functions g, which is f x b. Then the fx ab, fx means, this means partial derivative of f with respect to x at ab, this will equal g prime a. Okay, yeah, before break, let me make sure that we have this introduction first. So suppose that the function of two variables, suppose one of them we take as a fixed point, for example y. Let's say taking b as a constant. So let's introduce another function g, which is f x b. And if we would like to take derivative with respect to this x, then this is, we call this an f with a subscript x. We call this a partial derivative of f with respect to x. This is equal to the g prime a, which means this is going to be derived with respect to x. and y is just a constant. And this will serve, this definition will serve as our basis, especially for computational process in partial derivative. Okay. We're going to learn more how to take this definition into the limit as we did in calculus 1. But for now, we have two variables, which means it can be partial derivative with respect to x, and it can be with respect to y. Okay? So that will be for next week. And Tuesday we have a midterm. Or no, with midterm. Right?
Do you want to include this in an answer?
No. Okay, so after the break, we can have a practice for your midterm preparations, okay? So let's take a break for a while. Will be some exercise, okay? You can see first. And since the polar or parametric only the first question, let's try the first question first, okay? Let's try the first question. Just to review the parametric. Anyone want to try number one? Number one? Anyone? Maybe read the question first.
Which of the two?
I think 2 years ago. Yeah, 2 years. 3 years. Not yet. I will upload later. Maybe any request, which part should we take first? But maybe number one, okay, or two, because there's only about parametric only one in this case. And maybe if you have any other requests. Now, slope of tangent line, basically in parametric or in polar, you have a polar equation, and basically you could get this works by directly straightforward for the tangent formulations, or we could write uh, the, 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 the equation as in parametric. What does it mean? It means that we could always change the r into our parametric forms, or the Cartesian form. This is r cosine theta, y is r sine theta, right? And basically we can just substitute the curve. So x is 2 cosine theta plus this will be sine theta cosine theta, which is I will write as half of sine 2 theta from the double angle formulations in sine, and y will be 2 sine theta plus sine squared theta. Now I will write the tangent based on the definition in parametric. So dy over dx, this will be dy d theta, and then dx d theta. And basically we just derive all these stuffs. So dy will be 2 cosine theta and plus 2 sine theta cosine theta over the x will be negative 2 sine, and we have half here. This will be 2 multiplied by half, it's cancel, but we need to have the chain rule, which is we have the cosine 2 theta. We can simplify it and make this sine 2 theta. And that's it. I will stop here, and then I will take my theta and input into the equations. So input pi over 4. So pi over 4, this will be square root of 2, and this will be 1, right? And this will be negative square root of 2. This will be 0. So this will be our result. This will gives you negative 1, negative or we can rationalize and make it into that forms. So this is the result, which gives you B as the answer. Okay, that's for number 1. slope of the tangent line is, you remember that will be our gradient dy of dx. You could take it into parametric forms or using the dr, but I think it would be the same result. Both will be the same. Any requests? Which one we need to take? Which number? Anyone? Do you have requests? Huh? 5? Okay. 5. Yeah. Okay, 5 and then 2. Okay, let's say we are going to have 5 and then 2. Okay, so 5 and 2. 5, basically, we need to check every single series, whether they are diverged or converged, and then see the combinations in the answers. Which one is converged? So we can start from this A sine 4n over 4 with of n. Okay, so you have a power. Let me observe this. We have a sine, we have a 4 power n in the denominator. I think the best way to approach this, since this is a sine, means the maximum will be only 1. I think better to have a comparison, right? Comparison test. Well, let's check through comparison for A. We could take, suppose that we have, for example, we could imagine that this should be lower than this series, right? And this series here is a geometric, right? So this is geometric. R is less than 1, which is 1 over 4, which is, this is converged, right? This is converged. So you'll see that this should be converged as well. So converge as well. Converge by comparison. Okay. I hope you can write nicely. I didn't write very detailed, but I hope you can get the idea. This is geometric, and because the R is, the ratio is less than 1, it's 1 over 4. So I think it should be converged, and next one is also converged, and this is less than that. Okay. Next is B. This is also, we can have some comparison as well. So let me write here. So 1 over. And suppose that this is AN, and let's say we have BN is 1 over 2n, to say that the cosine have a maximum number 1, right? And this is a diverge because it's harmonic series, right? This, we can say this is harmonic series, so it's diverges. Okay. And then we could see that through the same idea of comparison test, this should be greater or equal 1 over 2n, right? The cosine has fractions, right? It has fractions. So that should be true. So that's why, since this is greater than this, and this is diverged, then it must be diverged as well. So this must be diverge as well due to comparison test. Oh, I forgot. This has something to do for number C. For C, it has a typo in the question. I forgot to write the ln here. So it's a wrong series. So C, number C should be having an ln. And this could be understood by telescoping sum. So by telescoping, we can rewrite the forms as n minus 1 over n. And then we can rewrite with the logarithmic property. Okay. So take some values for n. Taking from n equal to, this will be ln 1 minus ln 2. Okay, that's the first n, so this is n equal 1. And then plus, n equal 2. And then n equal 3, this will be 2 minus ln 3. And plus, let's say we take until 4. So 4 minus 1 is 3 minus ln 4. You will see that we are going to have this until we are going to get something that is going to be, this is ln. N minus 1 minus ln n. At some n. So at the end of the day, this will be resulting in, this will cancel with that, cancel. So canceling in between, you will have the both ends, which is the ln 1 minus ln n. And if we take our definition in limit, we are going to have a divergent series. So diverge. Yes? Yeah, I think we can. What the end is? Yeah, it's diverged as well. Yeah, it's okay. Yeah, I think we can also write this alternative. We can use limit comparison test. Yeah. Yeah, and actually, the limit comparison test is the official solution. This is actually alternative because we already have comparison. I would like to try something here. Okay, let's see one more. But of course, if this is only a multiple choices, and see the possible answer, which we have a divergence for the A is converged, B is diverged, and C is diverged. So B, C is diverged. So from the possible answer we have, it should be A and B. If it's only multiple choice. Okay. But I need some short explanation. Can we prove this B to be converged or diverged? And we have this square root in the top, which, if you remember, I think I have done this in similar question in class, or maybe do the same question. So we can take rationalization to make it in a full fraction that we can easily compare. So we can take the rationalizations, so rationalize the expressions, which means we take this and multiply with this. This is to help clear observations. Okay, we can get the clear observations. So we have n plus 1 minus n, and this will be so we have 1 over this, right? And then similar with the, let me move this going to the right. So from here, then we can compare. And we need to make sure that we have something to be compared with. So let's make something similar, but without the constant and in the bit in between. So this is n. So we need to compare with this. I think should be okay to be compared with. And of course, this is less equal, right? Less equal. Okay. And this form is 1 over 2 n with 3 over 2 as power, right? Which means that we can take the P series. So through the P series, this is greater than 1, which means that this is converged. And since it's less, then this is also converges by comparison test. So this is mostly done by comparison test for all the series here. Mostly can be solved through comparison test, either direct comparison test or using the limit comparison test. Okay. Okay, now let's try number 2. Number 2. Is there any question on number 5 here? I think mostly can be done with the comparison. This one? 1 over n. Okay, 1 over n. And using L'Hopital rule in the process. I think the same as we did last Tuesday. Oh yeah, yeah, yeah. Okay, now we take the number 2, which is this. Okay, let me write in the new paper to make it clean. So we have a function called ht is sine t over t. And we have this. T is positive, or it's not 0 here. And h of 0 is 1. And we have f of x, which is an integration with respect to t of the ht. And asking the f5, this means the derivative, the fifth derivative at x equals 0. Well, if you see this kind of question, this will be related to the Maclaurin. Remember, we have a coefficient in Maclaurin which is having this over the n factorial, or here is over 5 factorial. That's the coefficient of the Maclaurin. But we only need only this part. And our original function, it has this sign, right? It has sign, which is in Maclaurin, we could understood that as our reference. Okay, there are 2 ways at least to get into this question. The first is we need to have some familiarity with the function. If you can memorize easily all the basic function in Maclaurin, I think you could get this very quick. If not, you need to take some time to expand one by one from sine x and then getting into the series. It takes a while. That's why I'm suggesting maybe remembering the pattern. The pattern for the sign, if you remember, it has the odd power, odd number in factorial, and odd power in the coefficient, in the coefficient x, the x, right? In the x. So we can write first for sine, and then we define with x, so that we can be similar to our question here, sine t over t. Okay, we get the expression. So all the expansions is divided by x. So we reduce the power by x, and then by taking this integral, it means that this one, if we derive 5 times, well, we have an integration. The question should be asking about the original function with power derivative 4. And we integrate 1. Do you get my point? Okay. So let me write first. So the f of x is our integration 0 to x of h, right? And f prime is basically h of t, or x now. By fundamental theorem, this is h of x, right? Which means this is going to be sine x over x. And in Maclaurin, sine x could be written as, let me write the expansion. Okay? Let me write the expansion. All the odd for the x and the factorial, and it's alternating, sorry, it should be minus and minus. So sine x over x becomes, we are going to have 1 minus x squared over 3 factorial plus x with power of 4 factorial minus . Well, to convince, maybe you can make it into 7 or 9 power, just to see how it looks like. Well, the idea, so this is the f prime x. So I will write here, just to make it confirm, that the f-fifth derivative at x0, it means it is going to be the fourth power, or the fourth derivative. Of the f prime, right? Now we have f prime. So we need to find the f double prime, which we are going to just derive one by one. Okay. Oh wait, this is not 4. 5. Taking third derivative. This will be 1 over 3. This will be 3x squared we cancel 3, okay, and then f4 of x, this will be 0, and this will be 2x 5 to 1, cancel, and we have actually like that, right? So we have, this is basically the f five x is 1 over 5. Or here we have the 1 over 5 as our coefficient. So this is to be equal to 1 over 5. Okay. I think the other question, okay, right? Not too complicated, right? Number 3 and 4, I think should be okay, right? 4, yeah. Number 4. Okay, basically, I will just write some steps here. Radius or interval of convergence, it is about the power series, right? In power series, you will have a series which are about n, right? But it has also x. Okay? So we can see that the convergences is not about a single point, but rather a interval. So the best way to understand this question is we need to find whether, and we need to assuming that the series will converge at some point. And every power, it will be easier to understand the power through geometric series. And by geometric, which means that we are going to have a ratio that can be used for the determination of whether it is converged or diverged, right? So we can take this into ratio test. Okay. So take ratio test. So this is 2n plus 2. So we can cancel this with that. So this is x squared. So 3x squared. So this gives you result in terms of 3x squared. So which means that this will converge. So series converge when this 3x squared is less than 1. Or in our case, in our expressions, that x should be less than 1 over square root of 3. And this will be the radius. So radius is A. Oh, this is B, right? This is yeah, minus berarti for interval, but for the distance between the radius, right? The distance. Okay, if there is no further questions, I have a feedback for you. So